Welcome to part 2 of the lesson 4.4 tutorial video. In this video, we're going to look at converting mixed radicals and entire radicals from one form to the other, and then look at a word problem and how to put radicals in order from smallest to biggest. First, there are two ways that you can write a radical. A radical can be written as a mixed radical or an entire radical. Think of this like fractions. In fractions, you can write a fraction as a mixed fraction, say 3 1/2. That's a mixed fraction. An entire fraction that would be equivalent to 3 1/2 would be 7/2. Both of these are equivalent fractions, but there's two different ways to write it. Radicals works much the same way. A mixed radical has a product of a rational number and a radical. It's considered the simplest form of a radical expression. So some examples of that could be 3 times root 2. You could have 4 times cubed root of 6. And another example is 2 times the square root of x. When you have a big number written out front, you are timesing that coefficient by the root. The big number is just an integer, like 4, and then it's being multiplied by the root here. The 3 is not a coefficient, remember, it's the index of the root. So they're always being multiplied by the root. In an entire radical, we have a product of 1 and the radical. So basically everything is under the square root sign or the cubed root sign. So for example, if we have the square root of 32, we could write that as 1 times the square root of 32. That is a product of 1 and the radical, but we don't need to write the 1 there, so we just leave it out. Another example is the cubed root of 2 to the power of 5. Even though we have 2 to the power of 5, it's all under the root sign, and the 3 is the index, not a coefficient, so this is an entire radical as well. Now, let's look at how we can convert between the two forms. The first process we are going to look at is how to convert a mixed radical to an equivalent entire radical. There are 3 steps we need to follow, and step 1 is to write the rational number, or the whole number that's out front, as an equivalent radical. To do this, we use the same index as the radical that we already have in the expression. So we'll look at how to do that in a second. In step 2, we're going to join the roots using the multiplication property. The multiplication property just says that when you're multiplying two roots together that have the same index, you can join them together under one radical and multiply the radicands together. And step 3 is to simplify the multiplication under the root sign. So let's look at example A. 5 times the square root of 11. Remember, when there's a big number out front, that means you're multiplying the 5 by the radical. So what we're going to do is in step 1, we're going to write the 5 as an equivalent square root. So you can ask yourself here, the square root of what would equal 5? Well, we know that the square root of 25 equals 5. But how do we know that what this number is going to be under the radical if it's not just an easy number like 5? What we do is we take the whole number and we raise it to the power of whatever the index of the root was. So 5 to the power of 2, because the index of the root was 2. The square root of 5 squared is just equal to 5. But instead of simplifying it back to 5, because that's not the way we want to go to just a radical, is we write it as the square root of 25. And then we times that by the square root of 11. The second step is to join the roots into the same root. So we have the square root of 25 times 11 in the radicand. The last step is to simplify the multiplication under the root sign. So our final answer is the square root of whatever 25 times 11 is, and that equals 275. That is an entire radical that is equivalent to the mixed radical that we started with, 5 square root 11. Let's look at another example. Example B, we have 2 times the cubed root of 5. This time, because our index is 3, we need to write 2 as an equivalent cubed root. Well, we put the 2 under the cubed root sign, and we raise 2 to the power of 3. That will tell us the cubed root of what number would equal 2. And we're multiplying that by the cubed root of 5. Well, the cubed root of 2 cubed is the cubed root of 8 times the cubed root of 5. And when we join because we have the same index, we can join the roots together. So we have the cubed root of 8 times 5, which is the cubed root of 40. So that is your entire radical. That is equivalent to 2 times the cubed root of 5. Next, we have example C. We have 1.5 times the cubed root of 6. Here we're going to write 1.5 as the equivalent cubed root. So it's 1.5 cubed times the cubed root of 6. 1.5 cubed is equal to 3.375, and then we times that by the cubed root of 6. Now we have the same indexes on our roots, so we can bring them together under one root sign. So we have 3.375 times 6 under one root sign, and 3.375 times 6 is 20.25. So our entire radical is the cubed root of 20.25. In the last example D, there's a bit of a typo here. It's supposed to be 9 times the fourth root of 5. So we're going to use that as the example. So we have to write 9 as an equivalent fourth root. So we're going to have the fourth root of 9 to the power of 4 times the fourth root of 5. The 9 to the power of 4 is equal to 6,561. So we have the fourth root of that times the fourth root of 5. And to bring it all together under one root, we're going to have the fourth root of 6,561 times by 5, and that is equal to the fourth root of 32,805 as our equivalent root. That would be equal to 9 times the fourth root of 5. Just a quick note, make sure that you're writing the index on all the roots all the way through the question, and not to forget to write that index there, because we always have to indicate what our root is. The next process is looking at going the other way. It's how to convert an entire radical to its equivalent mixed radical. Remember, the most simplified form of a radical is considered its simplified mixed radical. So we're going to look at how to do that. Step 1 is to write the radicand as a product of its prime factors. And what we're doing is we're going to look for groups of the prime factors that make a perfect, square or perfect cube, whatever is the same power as the index of the root. So that's going to be important to look for. Then once we have those perfect squares or cubes or powers of 4, we split up the roots using the multiplication property in the reverse order of what we had before, or what we used before. So now we had multiplication all under one root, and we're going to split it up so we have a root times by a root, and they will have the same index. And then we can just simplify all the perfect roots that we brought out or apart. So if we look at example A here, we have the square root of 27. If you do a factor tree of 27, it will break down into prime factors of 3, 3, and 3, because 3 times 3 times 3 is 27. So we're looking for a perfect square here because we're using the square root. So I'm just going to write the square root of 27 as a product of its prime factors, 3 times 3 times 3. Right? That still equals 27. This is an equivalent statement. Now because we have a square root, we're looking for perfect powers of 2. So 3 times 3 gives you a power of 2, and we can write that like 3 squared times 3. 3 times 3 is 3 squared, and then we break apart our roots. So the square root of 3 squared times the square root of 3. In step 4, we simplify, and that's just we simplify the perfect square that we found. the square root of 3 squared is just equal to 3, and then we can't simplify this just the square root of 3 anymore, so we leave it as square root of 3. So 3 times the square root of 3 is equivalent to the square root of 27. Now, if we look at example B, we have the square root of 50, so we want to do a factor tree for 50. 50 breaks down into prime factors of 2 times 5 times 5. So if we write the square root of 50 as a product of its prime factors, we will have the square root of 5 times 5 times 2. Now I put the 5 times 5 first on purpose because that's my equivalent group of 2 that will make my perfect square. So 5 squared times 2 can be under the root sign. Break apart your roots, so you have the square root of 5 squared times the square root of 2. And the square root of 5 squared just will simplify, because it's our perfect square, just to 5. And then the square root of 2 we leave because it doesn't simplify anymore, and that is our simplified mixed radical. If we look at example C now, we have the cubed root of 48. So make your factor tree for 48 to see what its prime factors are. And we see that the prime factors of 48 are 2 times 2 times 2 times 2 times 3. Make sure you don't miss any. It's easy to miss one of the ends of the branches. You need all of them. And we're going to write the cubed root of 48 as the cubed root of the product of all of those numbers. So 2 times 2 times 2 times 2 times 3. Now because we have the cubed root, we are looking for perfect cubes. Now perfect cubes have 3 equal factors. So we need 3 equal factors of 2, and then we see we're left over with 2 numbers that don't make a perfect group of 3. So those we will be left with, and we rewrite this as the cubed root of 2 times 2 times 2 is just 2 cubed, and then anything that's left over we recombine back together, so 2 times 3 gives us 6. Break apart your roots for step 3, so cubed root of 2 cubed times the cubed root of 6, and the cubed root of 2 cubed, of course the cubed root and the cubed cancel each other out, so you're just left with 2. And cubed root 6 doesn't simplify anymore, so that's our root that we're left with. So the cubed root of 48 is equivalent to 2 times the cubed root of 6. Now I just want to quick compare that to the square root of 48. So the square root of 48, we don't need to redo our factor tree, but let's rewrite that as the square root of the prime factors, 2 times 2 times 2 times 2 times 3. And because we're looking at the square root, we're looking for perfect squares, or groups of 2 equal factors. And we see that we have 2 of those. So we can rewrite that as the square root of 2 squared times 2 squared times 3. Then the square root of 2 squared, right here, is just going to be, when we break it apart, we'll get the square root of 2 squared times the square root of 2 squared again times the square root of 3. And each of these square roots of 2 squareds simplifies to 2. So we are left with this one just equals 2, this one equals 2. 2 times 2 is 4. So we're left with 4 square root 3 as our mixed radical. So you can have more than one equal group of more than one group of perfect squares, just so you're aware, and that's how you can deal with them. We will finish example 4, parts D and E, and how to put radical expressions in order from smallest to biggest in a short part 3 video following this video.